Thank you, Hervé. Thank you to Muriel and Vasilisa for inviting me. I'm very pleased to be here. So I'm sorry that the slides are in French. I just didn't realize. I don't know that I would have had the time to translate them anyway. So today we're going to talk about meteorites and what they tell us about the origin of the solar system, seen really from the rocks that we get on Earth. Before we go on, I just want to show you this slide with shooting stars. I expect most of the people in the room have already seen a shooting star. Have you all? And do you know what happens? And it's interesting because in Corinne's talk, she talked about it this morning. Why does the sun shine? Why do the stars shine? It's because it's hot. What happens in a shooting star? Why does it shine? It's because something is hot. And what is hot, actually? It is that the air is being compressed by a piece of stone that goes into the atmosphere. And at first, it comes from the interplanetary medium. It's not dense at all. But when it starts going into the atmosphere is denser and denser and denser as you go down. So those rocks, they arrive at speeds which are 15 kilometers per second, typically. So that's extremely fast. They compress the air very fast. It doesn't have time enough to go away. So that air is compressed. It loses its electrons, makes a plasma, which is even hotter than the surface of a star like the sun. It's like 10,000 Kelvin, 20,000 Kelvin. So it shines. And you see the air that's running around the stone. So for that reason, even though the stone is very tiny, typically for a shooting star, it's a millimeter in size. There's a huge plasma that shines around it, that surrounds it, that you see. And the stone goes into the atmosphere. It's totally abraded by the plasma. It usually doesn't reach the ground unless it's big enough. And as soon as either it disappears or the air becomes so dense that the stone really slows down, then about 20 kilometers in height, an altitude is going to stop shining. So that's what you see when you see a shooting star. When it's a big object that falls, that arrives at the same speed, then it becomes very spectacular. And I'm going to show you a video of the arrival of the Chelyabinsk meteorite, which was back about 2013, so that's 8 years ago. That was very dramatic. I think most of you must have seen this thing. It's taken from cars, that's in Russia. A lot of people have cameras in their car to monitor what's happening on the road. And so we got a lot of videos of that object that arrives. So it's very dramatic. It shines a lot. So the camera is totally saturated, and then it tries to catch down, which is why it gets dark. But in fact, it's just the camera which is operating. So you see this very dramatic event. You see the light that's associated with the bolide. In the case of Chelyabinsk, we estimate that the size of the body that fell is like a big truck. It's about it's a little less than 20 meters in size. So, and arriving at, as I said, 15, 20 kilometers per second. I think it's very dramatic when you assist to something like that, but we'll see that later. Such objects that are 20 meters inside, typically they only happen like every 100 years or so. It's not very frequent. But one thing that is interesting is the object is being slowed down by the air, but also it arrives very fast. And what happens is at those speeds, it sees the air, even though it's a fluid, it sees it almost like a solid. So it's the same as when you are deep into a pool. If you go too fast and you're not vertical enough, you're going to squash yourself. In the very same way, the meteorite or the meteoroid tends to squash against the atmosphere, and it will break. And it will break sometimes several times in a row, but the first breakage is the one that's the more intensive, where it liberates a lot of energy, and that's what you see here. You see that the object is broken, fragmented. We call it catastrophic fragmentation. It has fragmented once here, but in fact the Chelyabinsk meteorite is going to fragment several times, 5 times, but it liberates a lot of energy at this time. And because the bolide is very fast, people saw the light, saw the fragmentation, and then the burst, which is a sound. It's about 10 times slower than the actual object itself. It arrives 1 minute after the event, roughly. And you're going to see 2 videos taken from the inside of a building where you see the object arriving, and you'll see the result of the explosion arriving. Oh, it's the same thing. It just explains how the object fragments, and the more massive objects go faster. They are less slowed down by the air. So in the end, the meteorite is going to spread over the ground, with the heavier objects at the front and the smaller at the back. Except because it fragments several times, you can have small objects in front of bigger objects because there has been several fragmentation. This is the fall of the Peekskill meteorite back in 1992. That was the first time we had a professional picture of a meteorite fall. So this just explains how things fragment and how they will distribute along a line that marks on the ground the direction of the object. So here is the picture. So you see the light, which shows that the bolide is passing. Then they've cut the video for about 1 minute, and then you're going to see the explosion. Look at this guy in particular. That's what happens, because it's a gigantic airburst that arrives. It's like an explosion, and we'll see afterwards what happens. So this just plays on and on, okay? And the next video is even more dramatic. The people, they're just walking out of a factory in the morning, and they don't know what happened, and they just walk out of the building. It is not a very sturdy door. Still, you can see it's a very big burst. Nobody was really severely hurt in that accident here. But in fact, with the whole Chelyabinsk town being under the explosion, basically half the windows of the town were exploded. And there were about 1,000 people who were injured. 2 of them really, really severely. I know that one woman, she was thrown down on the stairs. She was in a staircase, and she fell, and she really hurt her spine. I think she broke her spine. I know there was another person really severely injured. All the others, they were just watching this thing and looking at the trail of dust behind that was left behind the meteor when the explosion arrived, and they were in front of windows. The windows exploded in their face, basically. So there was about 1,000 people injured because of that had to go to hospital. This picture I like very much. I've taken it simply from Wikipedia. It's the theater at Chelyabinsk the day after the event. And what I really like is the face of the cleaning lady, and she said, where am I going to start with all this glass all over? Half the windows in Chelyabinsk were broken at the time. And what was funny is also it fell on a day where there was, we knew that a small asteroid was going to come close to the Earth. And there was some confusion for about a day till it was realized that Chelyabinsk came one direction. In fact, it had not been seen at all. It was coming from the direction of the sun. And the asteroid DA14 came from a totally different direction. So the two just happened to cross the path of the Earth. One of them missed it, but they just happened the same day. And after the fact, they found in the snow, they found those rocks. Here is a meteorite. We'll come back on that. That's inside a pocket of snow. And this is the inside of the meteorite. And you can see what's called the fusion crust. That's the part where the rock interacted with the plasma in the atmosphere. That was really, really, really hot. So the rock is melted. So you've got a thin layer of melted material at the outside of the rock. How often and how catastrophic are such events? Here we have, it's a log-log diagram, and we're looking at the number of events per year as a function of the size of the impactor. And here we look at the size of the destruction it causes. So you can see that particles which are a centimeter in size, basically there's about 10,000 of them which encounter the Earth on a yearly basis. But the bigger the rock, fortunately, the more rare they are, and we are lucky about it. And at the bottom of this scale is objects which are several kilometers in size. And this is the meteorite that created the Chicxulub crater 66 million years ago, sorry, which you'll hear probably later in the talk about impact. And so typically a rock about 20 meters in size, the size of the Chelyabinsk meteorite, happens roughly every 100 years. And typically it will create destruction locally. I'm not talking of the burst, I'm talking of the destruction. Typically it will create roughly on the order of 10 meters. But clearly the bigger the object, and it can create destruction at the size of a planet if you have a body which is tens of kilometers in size, whereas much smaller objects will create destruction at the size of a house, basically. So these things are not very frequent, thanks for us, and we are very protected by the atmosphere. Most of the rocks, they fragment in the atmosphere, and then they do not reach the ground, or they reach the ground only a small fraction. Even in the case of the Chelyabinsk meteorite, so we estimate 20 meters the diameter of the objects, that's 10,000 tons, and what was found on the ground is about a ton. All the rest was vaporized in the atmosphere. So it will eventually recondense and fall on Earth, but it will contribute very slightly to the mass of the Earth, but it will not create any more destruction that has happened already. Just to look at something a little bit bigger, something that's about twice the size of Chelyabinsk, I mean in size, so that means in volume, it's because it's to the cube. In volume, that means about 10 times the mass and the size and the volume of Chelyabinsk is the event of the Tunguska, which it typically is the type of event that happens every 1,000 of years. In that case, it fell a little over 100 years ago in 1908, and it created destruction at a much bigger size than Chelyabinsk, and that was in a very hard to reach region, so people only went to the site 20 years after the event, but they could see all the trees that were felled from the epicenter in a radial way around the epicenter. And this is a description of what happened, and I really like that slide, also from Wikipedia. Here you can see where the the Tunguska event happened, and the little red dot in the center is the zone that was destroyed, where you have the tree that have fallen. It's a radius of 20 kilometers. The pink around it is where the destruction was heavy. It's in a radius of 100 kilometers. And then the noise from the explosion was heard 1,500 kilometers around it. So that's really far. So that's one thing. It gives a good idea of what happened in that case. But also what is very striking about this thing is you can see that if the bolide had fallen like 3 hours later, it would have been St. Petersburg, Copenhagen, all these regions, which is densely populated, which would have been under the burst. Whereas Tunguska happened in a forest where there was just basically mosquitoes, so nothing really happened. That people in the nearest towns, they could feel the burst, basically, and some of them were thrown on the floor, but it didn't go any further than that. So if the object is even bigger, obviously it will create even more destruction, especially if the object is not fragmented, not destroyed by the atmosphere, which is often the case if you have a big iron meteorite. It's more compact, there is less, the material is less easily broken, and it can reach the ground directly with most of its energy. It has lost very little in the atmosphere, and then when it reaches the ground, it's going to brutally liberate all the kinetic energy it's carrying, and then the explosion will take place on the ground, and then that's when it will create an impact crater, which you will hear a lot more about in the next talk. So this is the first crater that was identified as a crater roughly 100 years ago, and this is above a kilometer in size, but the size of the impactor is about 40 meters, 60 meters, so that's really what's in the center here. it's only about 100 years ago that, I mean, it's even less than that. It's really, there was a debate as to the origin of these craters for a very, very long time. It's only when people went to the moon that they definitely were able to say everything is impact at the surface of the moon, and this is something that happens because bodies fall on other bodies. But before that, there was really the astrophysicist thought the impacts were coming from the ground. Basically, it was a geological process, whereas the geologists were saying it's something that has an astronomical cause, because people couldn't figure out, they hadn't realized how much energy would be carried by rocks that would be falling on top of the Earth. This process of crater forming is basically the end of the formation of the solar system, because the object grew and grew from what we call the accretion, which is the gathering of bodies together. And this is a representation of the latest event that happened, latest major event that happened when the planets started to grow and grow and grow and clean up their area. Well, at some point in the area where the Earth now is, there were two big bodies, and the two of them collided together, and one of them became the Earth, and that one, which is about the size of Mars, collided with the Earth. And this is an old representation. Now people think that most of the object was vaporized and there was a mixing between this material and that material, and part of this material went in orbit and gathered to form the moon. So that would have been a very, very dramatic event, and at that time it is believed that the surface of the Earth would have melted basically over a large thickness, which is really important, because that means that water or organic material that might have been on the Earth at that moment, they basically got destroyed. And if we want to make life, we will need to bring back these elements later on, which we will discuss later. So the surface of the moon is totally covered with such craters. This is the face that we are used to seeing, and this is the back side of the Earth. And as I said, the astronomers, they really discovered that there was impact at every level when they look at the Earth. And that is the reason where the soil of the moon is so fine-grained and that the steps walk on it. It's because that is what we call cosmic gardening. There is always particles and micrometeorites falling at the surface of the moon and impacting. And because the moon has no atmosphere, whatever the size of the object, it will fall with its full speed, and it will create a crater which is roughly 20 times its size. So basically, the surface of the moon is constantly bombarded, and this is this is part of the construction of all the bodies. The Earth doesn't live that, because the Earth is protected by its atmosphere, basically. This is also important because it's when such impacts happen, sometimes part of the body which is impacted will escape, will acquire velocities that will allow it to escape its body, and that's because of impacts at the surface of the moon that we now are able to find lunar meteorites at the surface of the Earth. So a small summary. So this is what we call a meteor, which is, or a bolide when it's very intense. So that's the phenomenon that you see in the atmosphere. And when the stones fall, they fragment inside the atmosphere, and they will deliver the remaining stones on the ground. This is the distribution of, roughly the distribution of stones which were found in Niger. And the guy who found those stones really searched the area, went several times to pick up more stones and more stones. And they were distributed over 40 kilometers, but he chose to just gather them together so that we would see what they look like. The biggest ones, they're about 30 kilos in size, so they are objects about that size. And there are truckloads of little ones, like there was in the case of Chelyabinsk. Before we go on, just like Corinne did this morning, I want to go through a little bit of history, what we know, and it's, in fact, you will find out that as a scientific discipline, the study of meteorites, which we call meteoritics, is a fairly recent scientific discipline. For a very long time, there was no question. People just saw this and they thought that's a prodigy, and they thought it might have a meaning. This is what happened in the case of the NC meteorite, which is the oldest meteorite that is curated, that we kept the stone of, the description and a stone of in Europe, because now we know there's an older one in Japan. And at the time it fell, Sébastien Brand, who was a poet and rector of the academy in Bâle, in Basel, he produced this poem. He wanted to tell the king of Austria, who was also the king of Alsace at the time, to go at war with the French king, because the French king had done something really nasty to him. So he produced this leaflet, which I think is very interesting, because it's one of the first, whatever you call that, when you hand out documents. Now we do this in large numbers, but at the time there was just after the printing was invented, so they must have produced, not many people were able to read it, basically. So they must have produced about 100, and these were distributed, and it explained that it was a good omen, and that the king of Austria should go to war with the King of France. And it was illustrated by this little cartoon. It's also one of the first cartoons of history. And what I find is interesting, so you have the town of Ensisheim. They show two people here attending the event. In fact, there was only one young shepherd who attended the event. But what I find interesting is you can see the stone in the sky and you can see the stone in the ground. So that's to give you the idea of the motion, that the stone has fallen from the sky. So for Sébastien Brand, that was a good omen, and the King of Austria did go to war with the King of France and won partial reparation. But what's interesting is about 50 or 60 years ago, afterwards, in Italy, in a chronicle, they used the event and they showed that 1492 was a very, very bad year. That was a very bad year for several reasons. One of them is the Borgia got to be Pope. The first Borgia got to be Pope. The French invaded Italy, and America was discovered, from which they brought back the syphilis, which was a nasty disease. So clearly it was a bad omen. But what's interesting is they took that same cartoon and they didn't have Photoshop at the time, but that didn't prevent them from changing the cartoon. So you can see birds dying. You can see, maybe, I don't know whether you can see it, but there's the head of a devil in the very, very dark sky. There's a dog that's hiding. There's a salamander, which is a fire animal, which reveals danger. And there's an owl on the town, which also shows that it's a bad omen. So even at the time, they were using the event as a prodigy and having a signification. And for many, many years, people did not doubt that there were objects falling from the sky, and that was a prodigy, and it didn't go any further. With the era of the light era, I don't know what it's called, l'ère des Lumières in French, I'm not sure what it's called in English. People started ordering the world, basically, and saying, this is supposed to have fallen, but we know it's a fossil, this is a concretion, this is that. So they started doubting that they were actually rocks that fell from the sky, sorry. And then there was really the scientific study of meteorites starts at the end of the 18th century, where academicians were studying a couple of rocks falling from the sky, and they could see that there were relationships between them, but they thought it was just a coincidence. But these rocks had been hit by lightning; it was nothing else than that. So they said, well, maybe we should study this more. But they still didn't believe in the fact that rocks could fall from the ground. And things really started moving very, very late, 1794, when Chladni, who was a physicist, who was a specialist of sound, started saying, we really have no idea. There is no reason that we can say whether these rocks fell or whether they didn't. But what struck him is the description of stones falling from the sky were very similar at different time, different region, and always people describe basically the same phenomenon. And he said it couldn't be proved that nothing was falling from the the sky. And that's when the idea started to change. Plus there was a couple of very, very spectacular falls in Italy, in England, and people started really studying them chemically and closely. And what they discovered in all those rocks that were supposed to have fallen from the sky, they all had this common thing, that they had metal inside them. So you have to understand, it's a mineral that's shiny. It's like a pair of scissors, or just like this. This is shiny. Normally there is iron in most stones, but it's associated with oxygen. In this case, you've got metal grains, and not only was it iron, but that iron was associated with nickel, which was a chemical element which had been discovered just very recently. And all of these rocks had that. And normally, most of the time, no rocks that at the surface of the Earth, we'll discuss this afterwards, has metal that way. So that's when the idea really, really changed. And then there was the fall at L'Aigle in 1803. And the Biot, who was a physicist, went and really studied all the rocks, all the area, and the distribution of the rocks in the area. And he's drawn the first ellipse that shows how the stones really distribute. And he had a report at the French Science Academy, which really explained how those rocks had actually fallen from the sky. And that's when the scientists changed, really, and everybody was convinced, but not everybody. It's stupid because I've translated this into French. It was originally in English. It's Thomas Jefferson, and he says, I don't think it's very surprising that there should be stones that fall from the sky in France. There are many true philosophers in France, as many as otherwise, but they also have a lot of imagination, and it probably can give them facts that actually did not happen. So they are capable of believing just anything that's really, really stupid. I don't think our American colleagues would say that now. I should hope not. Anyway. So these are two meteorites. We now know that they are fallen from the sky, and because Europe, and in France in particular, were the first regions where these things were really recognized, we have historical collections, and these things are not found very, very frequently, even in France. During the whole 19th century, which is the moment stones were recognized as meteorites, to the end of the 19th century, we basically recuperate one stone every other year, which is very few compared to what is actually falling. And from the 20th century, it's more like one stone every 10 years that we actually recover. That's because it's difficult to actually see them fall and recover them, and people are not living outside as much as they used to, so they don't see them fall, they don't find them. But we'll discuss that later if we have a little bit of time. What we will discuss today is, why do we study meteorites? What do they tell us? The first obvious thing is the fragments from rocky bodies from the solar system. So you have here a very bad diagram of the solar system, which shows, but its interest is to show all the bodies that we know, clearly all the planets, and then there are rocky bodies called asteroids, which gravitate somewhere between Mars and Jupiter for most of them. And then further, there's the location, and much, much further, of course, there's the location where you have icy bodies. Some of them sometimes go inside the solar system and become comets. So meteorites fall from most of these, from these bodies, from some of these bodies. And what's interesting is we have visited most of these bodies. We've sent probes, mostly on each of the planet has been visited by a probe. But actually landing, we have not landed on that many planets. We've landed on 1, 2, 3, 4, 5, 6, 7, 8, 9 bodies right now, because it's much, much more difficult to land on a body than to actually visit it and fly by it. So there's only 9 bodies, including the Earth, on which we have actually landed. And then how many do you think we have brought back samples from? 2? No, a little more. A little more. We did not bring. We have samples from the Earth. We brought 380 kilos of lunar samples from 3 types of missions nowadays. We brought back some rocks from two, and soon we hope 3 asteroids, and we brought some particles back from a comet that were sampled from the atmosphere, basically around the comet. We have access to samples from 1, 2, 3, 4, 5. We hope 6 bodies. With meteorites, clearly, we have a lot more material. We have as much material, basically, from lunar rocks that have fallen to the ground by chance, almost as much as we've brought back from missions. We've got material from Mars, because we have sent several rovers that are on the surface of Mars, but we haven't been able to bring back samples so far. And we probably have in the form of micrometeorite material from comets. And obviously, we've got thousands of tons of material coming from a variety of asteroids, which are accessible to us. So first thing is meteorites. They are samples of the outer of the solar system, so they are space samples. Second thing is, I should have started this. Second thing is, some of these meteorites have come from bodies which have been very, very little transformed, this area. It's a representation done by a painter who is also an astronomer, which really helps him describe context for things. It's a representation of what the solar nebula might have been, the protoplanetary disk, where you are seeing the sun here and you're orbiting around the sun among the stones and gases. And it has the same problem of representing something like that, gives you a very bad idea or a very good idea of what it was, because it's the same as the drawing I showed you earlier. You cannot represent the solar system at scale. With the distances and the bodies at scale. It's the same here. It gives the idea that it's a very, very dense material, very, very dense medium. It wasn't like that. It was obviously, things were much more separated or much, much smaller. But still, it's the best representation we've had for a long time of what the solar system might have been like. So with the accretion taking place in that disk, and some of the bodies that are now asteroids or comets, they have very, very little evolved since then. And when you find meteorites that come from these bodies, then they are probes of what took place in time, and we have a picture of what was taking place in the forming solar system. So that's why meteorites are one of our best sources of information as to what happened at the time. There are 2 really main groups of meteorites. Earlier today I said that meteorites were identified because people could see that there was metallic grains with iron and nickel inside. And I said earlier that rocks normally at the surface of the Earth do not contain iron in metallic form. This is why we have what we call the age of iron. That is because in order to make metallic objects, you have to be able to extract the metal from separate the iron from the oxygen in which it's associated. And this is what we do in the sidérurgie, in the furnaces, in high furnaces. You put your iron ore, in which oxygen is associated with the iron, with the source of carbon, and because carbon has more affinity for the oxygen than the iron, then carbon is going to go away as CO2, and then you're going to recuperate the iron at the bottom. Of course, I've simplified it. And people have only known how to do that for about 1500, I mean, in Europe and Africa, for about 1500 1500, yes, 1500 years before our era, so it's not that long. And mostly, for a very long time, when they had iron, it was iron from meteorites, basically. So you have at the Bronze Age, you have weapons in China, you have a dagger in Tutankhamun's tomb. All these things, they were made from iron meteorite, because it's much, much easier if you've got a meteorite that's all made out of iron, metallic iron. You just need to heat it and bang it and fragment it, and then you can work the iron, and then it's easy to have a metallic object. It's the blade that's totally rusted that was made of meteoritic iron. But at the surface of the Earth, there is normally no iron. And why is it? That is because after accretion, the Earth was hot inside, and the heat, which was the result of radioactive decay from elements which were formed in stars before the sun was formed, was heating the center of the body. And if you take a material that's made of silicate material and metallic material and you melt it, you make two immiscible or several immiscible liquids, and the denser material is going to go at the center of the planet, exactly like when you have oil and vinegar. The oil is going to be above the vinegar. In the same way, the vinegar will go at the bottom. The liquid iron is going to go to the bottom of the planet, while the lighter liquids are going to erupt at the surface. And this is the way you make bodies which, like the Earth, have a metallic core, a silicate layer with the less dense liquid, mostly basalts, and then you've got a residual mantle in between. This process isn't finished on Earth because Earth is still hot inside, and it has, this is why we have volcanism. This is because the lighter liquids erupt. And what are the elements that do that is the radioactive elements, and this is all the radioactive elements that are involved in geology. And here they're all ranked like that, and this is their half-life. And you've got elements which have a very, very short half-life, typically for aluminum 26, 700,000 years. And then you've got things that are called that are in billions. And these different elements have a different role in planetary differentiation. The very light element, they're going to give a lot of heat very, very fast, especially aluminum, because it's an element that's rather abundant, so it's going to give a lot of energy very, very fast, but it will not last. But as aluminum 26 stops operating, it's heated the planet, then the lighter elements, the elements with a longer period are going to take the relay, and now what heats the Earth is no longer clearly those elements, but it's those elements like uranium, rhenium, and so on, which are decreasing really, really gently. It's like you've had a very bright fire, and then you've got the embers that are still going, and this is the situation with the Earth, where there's still heat being produced in the center of the Earth. So there are two kinds of bodies, those that come from planets which have melted, just like the Earth, and because those planets can be broken, you can get samples from the center or from the surface of such planets. And then there are the planets that in which melting hasn't gone to completion, and then they're going to tell us more about the story of what happened in the protoplanetary disk. This is what happened with the Earth differentiation. It happened with a few asteroids where you had differentiation, and then when you had impacts, sometimes you could go deep inside the asteroid, and you could have pieces of the asteroid that would fall, or a body that were totally broken. This is how we can find pure iron meteorite coming from the center of a body that has been destroyed. There are bodies which accreted late, when the aluminum 26 had already decayed in the gas gas, basically. So this did not accumulate as much heat as the bodies that were formed early on. So this did not melt inside. And so you get meteorites that come from bodies which have not totally melted, which is what we call primitive meteorites, chondrites. And these constitute most of what falls on the surface of the Earth. Presently, it's about 86% of the objects that fall. And then there are basaltic rocks or metallic rocks, which constitute about 12% of what falls on the Earth. So clearly, they give us totally different types of information. Those that come from bodies which have not melted give us information about the genesis of the solar system. And they are distributed into different kinds. Most of those that fall are quatordinary chondrites, about 80% of the rocks that fall, so it's really a lot. But then we've got two varieties of chondrites. We'll come back on that later on. Some which are very rich in carbon, which will have more interest, which are more interesting to us in terms of the origin of life, which are only 3% of the rocks that fall. And then there's also 3% of rocks which are really, really highly reduced. And in terms of isotopes, really look like the Earth, and we wonder whether the Earth is made from similar material as those. Anyway, those rocks really tell us about the genesis of the solar system, and we'll come back on them later on. And then the differentiated rocks tell us more about the internal evolution of planetary bodies. And so when these fall, we obtain metallic meteorite, basaltic meteorite, meteorites which contain silicate, olivine, so mantle, silicates, and metal, which in first approximation could come from the limit between mantle and core. In fact, we think that's not the way they're really actually formed, but we'll discuss that later if we have a little bit of time. And then we've got those rocks that come from primitive bodies which have not melted. And I'm going to talk about both now. So this is a rock, this is a chondrite. You can see the metal grains that are shiny. All the little white grains are shiny. So you have a mixture of metal and silicates. And if you orient it in a slightly different way, you're not going to see the metal shining, but you can see all these little spherules which constitute the rock. Most 85% of the material of that rock is made of that little spherules, which we call chondrites. This is the shape. This is a little piece of a chondrite that was broken and looked at in the electron microscope to show you that in fact the rock is made of those little droplets, solids that have solidified clearly, which are stuck together and which make up the bulk of the material. So chondrites come from bodies which have not been melted as a whole. Chondrules individually have been melted, but the whole rock and the whole body from which the rock fall, they've preserved the texture which they had in the protoplanetary disk. And so they tell us about the early episodes of the formation of the solar system, while differentiated bodies are really apart from that. And they will tell us about the internal evolution of planets, crust, mantle, and core. So in the old days, if you see old literature about meteorites, they're going to talk about stones and irons or iron meteorites. I think this distinction does not make sense anymore to talk about stones, except if you're talking about the physical properties when the body actually crosses the atmosphere, because whether it's a chondrite or an achondrite, it is not, or basalt, it's not going to make any difference. But I think what's the distinction that's really important is between primitive meteorites, also called chondrites, and differentiated meteorites, which come from bodies which have been melted. So let's look at the space a little bit, what they tell us. As I told you, it's only in very, very beginning of the 19th century that people admitted that meteorites were stones that were falling from the sky. It's also at the very beginning of the 19th century that the Ceres asteroid was discovered by an Italian astronomer. And very early on, I have read, I cannot locate that reference anymore, but I've read that Chladni, who was the one who said meteorites from the sky, he said they come from those bodies when they were discovered, but I cannot find that reference anymore. So how do we know that we have fragments from asteroids? How do we connect? And how do we know which meteorite comes from which body? Here is a picture of a thin section of a rock that's from Vesta. What information do we have? We look at spectroscopy, so we can look at the light from the sun that's reflected by the surface of an asteroid, by the surface of asteroids. Here, asteroid Vesta, but then you've got other asteroids which reflect the light. You can look at individual minerals, light them with the light that's the same as that of the sun, or you make the appropriate transformation. So you can look at the individual minerals. How do they reflect the sunlight? And you can see, for example, that pyroxene is a spectrum that's very similar to that of Vesta. So you can have a good idea that there'll be pyroxene inside Vesta. And the other thing you can do is you can crush meteorites and look at their spectrum when you light them with sunlight, and in the same way, and you can compare the spectra of those bodies of meteorites with those of asteroids. This was done first in the 70s for Vesta, and then that's when people started to say, well, these category of meteorite, we call eucrites, all those basalts and related rocks, they have to come from the asteroid Vesta. And since there has been some more meteorites that were attributed to different kinds of asteroids based on their spectra, but we'll see that it's something that is that we're doing, but that isn't very, very precise. Obviously, it's much better to go and visit the planets, as we did for Vesta. This is a relief map that was made on Vesta through the Dawn mission, and through studying this kind of rock, eucrites that we have on the ground that we think are all emitted from one of these craters. Then we can try to study the geology of Vesta. For example, we have this rock, which is typically a basalt, and then we've got this other rock, which is, in terms of isotopes, is very similar. So we know they're related. We know these come from the same body. So the question, but this is accumulate. That means it's a rock that has taken time to crystallize at depth. So what's the relationship between those two types of rocks? The simplest idea is you've got the basalt that erupted at the surface of the planet while you had accumulate underneath. This is this region. But when you study these two rocks chemically, you can see that this rock, in fact, has been contaminated with liquid that came from a rock like this. So that means these rocks have been put in place as intrusion inside the basaltic crust. So by studying these meteorites at a distance, even though we did not bring back samples from Vesta, you can try to study the geology of that planet at a distance. Obviously, it's something that is long and difficult and not very precise. The best would be to actually bring back rocks from which you would have the geologic context in which they were picked up, but obviously this has been done only for the Moon so far. On planet Mars, also, we can try to study from meteorites. Once again, the best would be to bring back samples, but as you all know, it's difficult. When I started my career, we were going to bring back samples from Mars in the early 2010s. If we have them in the early 2030s, I think we'll be really happy. It isn't something that is easy to do. Nevertheless, on the day Curiosity landed on planet Mars, we had been studying this rock, and we thought it was different from all the rocks that we knew. And we realized it was coming from Mars the day that Curiosity landed. And I spent the fall of 2012 studying this rock, while my colleague Violaine Sauter, just a floor underneath me, was studying the rocks with Curiosity. And it was a very exciting period, because I was said, we've got feldspar in that rock. And the feldspar is a silicate that is not normally, it's the product of differentiation towards when you go towards the granite, when you have more siliceous liquids. And so it's a product of planetary crust evolution, and we've not seen them in meteorites so far. So that was the first time we had actually feldspars like this one, potash feldspar inside. I was very excited, and Violaine was telling me, you know, we've got potash feldspar on Mars. I said, we've got them in our rock. And then she was saying, we've got phosphates, and we've got phosphates too. So we were comparing notes the whole fall. So that was very exciting. It was also very exciting to find zircons inside these rocks. And those of you who are geologists know that zircons are used to date rocks. And those zircons on Earth, the zircons are isolated, so they're detritic. They're found in sediments, the oldest zircons. They are 4.3 to 4.4 billion years on Earth, mostly 4.3, even though there is some 4.4 billion years ago. Inside that rock, they're associated with little bits of rocks. So we were very excited. We thought we were dating these rock units. So we had older rocks from the crust, from a differentiated crust on Mars, than we could have on the Earth. Now, Virgile has been working at destroying our hopes because Virgile has been finding that all the zircons, they are broken, they're missing a part, so they're probably older than, I mean, what we date is the zircons themselves, but it's not the rocks that are around them because they're probably posterior to the formation of those zircons. So anyway, those zircons can be used to date something, some crystallization of a rock. And what you have here is an isotopic diagram where you have lead-206 over uranium-238, from which it's the decay product, and here lead-207 over 235 uranium. The interest of the uranium-lead chronometer is you've got two different isotopes of uranium and two different isotopes of lead, which are the daughter products of those uranium isotopes. And if nothing happens, these things should decay at rates which are always the same. And you can normally, as a function of time, a rock should follow always this curve in terms of the decay of these two elements. So if a rock is 4.5 billion years ago, it should fall here. And depending on where it falls, the comparison of these two ratios, because they do not decay at the same time, is going to tell you the age of the rock. But if the system is open, either you lose, if you lose lead in particular, it's going to have the same effect on the two isotopes. And for that reason, instead of following the actual decay curve, you're going to go along a line. And what we can see simply from studying those zircons is that they crystallize roughly 4.5, it's actually 4.42 billion years ago, but also the zircons were perturbed by probably a shock or alteration or whatever. Virgile's working at it right now. And even in sectors of some of those zircons, you can see that they fall inside those lines. And the magic of this Concordia diagram is where this line intercepts the Concordia curve, you can tell when is the perturbation, and the perturbation, it wasn't very precise in our first measurements. It was 1.7 in the paper was first published, but we now know that it's more like 1.5 billion years. It's a little more recent. So just from studying these minerals, you can know that there was a crust that had started to differentiate on Mars 4.4 billion years ago, and this was perturbed in this area. It doesn't mean that it applies to the whole planet. One has to be very careful, but that was very perturbed 1.5 billion years ago. So you can see, just from studying those meteorites, unfortunately, we don't know exactly where they came from, although we do have an idea for that very rock. But just from studying these meteorites, we can do geology and try to reconstruct the study of Mars. But actually, the connection in these two cases, whether it's Vesta or whether it's Mars, the connection between the planet and the rock is fairly easy to make, but often it isn't that easy. And we have many cases where it's very difficult to actually make the connection between a rock and the type of asteroid. And for example, we have here the reflectance spectrum of ordinary chondrites, like this one. And people for a long time thought they were coming from S-type asteroid, but you can see that the spectrum is similar, but it's more oblique, it's more vertical. In fact, it's redder because we're going towards the red. And for a very long time, people really agonized and fought. It was when I started my career, people were really fighting very, very hard with those who thought that these ordinary chondrites were coming from S-type asteroids and those who disbelieved it. And in fact, one had to go to a first asteroid, bring back the first samples from asteroid, which had a spectrum like that. But it turned out that the rock that were brought back by the Itokawa mission, Hayabusa mission, Itokawa was the name of asteroid, they totally look like ordinary chondrites. So that really ended up the debate. Asteroids, the surface of asteroid is being modified by the cosmic gardening and the irradiation per particle, so it ages the surface, makes it redder as far as ordinary chondrites are concerned, because other material may react differently, and that's why there is such a difference, but in fact those rocks do come from these asteroids. Most meteorites were capable of making a connection between a type of asteroid where they came from, basically. About 98% of the meteorites that we observe that fall on the Earth, we can tell from what type of asteroid, not what asteroid, what type of asteroid it comes from. But you can see that inside the asteroid belt, it's only about 30% of the asteroids that are in the asteroid belt that we have samples from. There's about 70% of the mass of the asteroid in the asteroid belt that we have no samples from. Of course, this is highly biased because the biggest of all asteroids is Ceres, and we have no sample that come from asteroid like Ceres. So most of the mass of the asteroid belt, we don't know what it's like. This is a little schematic diagram of all the type of spectra of all the asteroids that are known, where you can see S is where the ordinary chondrites come from, and it's all just little schemes to recognize this. And there are 6 types of asteroids for which we have no samples on Earth, as far as we can tell. And in fact, the 2 missions that went to asteroids very recently, they've picked 2 of these carbonaceous type of asteroid, B and CG, to bring back samples from. And we already know that, I can't remember which one is which, but the samples from Ryugu have come back already. In fact, they really look like CI chondrites. And also, we think that a large fraction of the material that comes back from, that falls from the sky doesn't fall as big meteorite, but as micrometeorites, as small dust. And we think these probably are more representative of these asteroids that we are missing, and that interplanetary dust particles are the best analogous material to those asteroids which are not sampled in our collection. Now I'm going to talk a little bit about how we use meteorites not to sample space, but to sample what took place in time. And in fact, this is the Orgueil meteorite, which is a CI meteorite. And Corinne talked about this this morning. She showed you this diagram. This is the abundance of elements. This is a log-log diagram. It's the abundance of elements inside this meteorite and compared to the abundance of elements in the sun. And you can see that there is a very good agreement between the abundance of those various elements. Sorry, I should say in the sun is mostly hydrogen and helium. So if you want to make comparison, you have to ratio it to one element, and we are ratioing everything to silicon. So for one atom of silicon in the sun compared to one atom of silicon in the rock, and the ratio of all elements to silicon, it's basically similar of really several orders of magnitude, except for the most volatile elements. Carbon and nitrogen are more abundant in the sun than they are in the meteorite, and of course there's a huge difference between for hydrogen and helium, which are all the elements that do not go easily in the materials. What has to be remembered that 99.9% of the material of the solar system is in the sun. So when we talk of the composition of the sun, we're talking of the composition of the solar system. Most of it was formed in the Big Bang as in the form of hydrogen and helium. And everything else constitutes in the protoplanetary disk, everything that constitutes the gas and the grains was formed in stars that died before the sun was formed. And mostly these grains, they were condensed either in the interstellar medium or at the vicinity of stars. And all of these things Corinne talked about very, very in a lot of detail this morning. But what's important is the sun was formed from the interstellar medium, which had been fed basically from all these stars with different evolution, which created all these heavy elements. What we're interested in is this part of the story, and basically the composition of the interstellar medium has been changing with time. Corinne told to us about the galactic evolution, but that's really what's important, is at the time of the Big Bang, basically the first stars that formed were comprised mostly of hydrogen. But with time, the medium has been evolving, and it's kept evolving. But what we have with Orgueil and with the meteorites that we fall are the composition of the interstellar medium 4.5 billion years ago. That's what's really important. That's the composition of the interstellar medium 4.5 billion years ago. This is what we find in the meteorite Orgueil. Also, only Orgueil actually has this composition. Every other meteorite, if you look at its chemical composition, it's different because it's lost some of its volatile elements. So this is what the diagram on the right here shows. We're looking at the ratio of one element to aluminum, which is the least volatile element of this set, in different categories of meteorite. And the more volatile an element is, the more it is depleted in all the other rocks compared to Orgueil. So CM has lost, for example, 60% of its zinc compared to Orgueil with respect to aluminum, and CO, CV chondrites have lost 80% of their zinc. So the more an element is volatile, the more it is depleted in different categories of rock. So that shows us that in between different bodies that form in the solar system, there was fractionation in terms of a volatile element that was due to lack of condensation or loss of volatile element through evaporation. So only one category of rock really tell us what the composition of the nebula was 4.5 billion years ago. All the other rocks, they are close to that, but they have evolved in processes that if we can understand them, they're going to tell us what was happening, what was taking place in the protoplanetary disk. They also show differences in terms of texture, chemistry, isotopes, but also in terms of texture. This is just to show you three thin sections seen in polarized light. It's like looking at a stained glass window. You're looking at a very thin slice of a rock with the light behind it, which is in addition polarized and which you analyze in front of it. And you're seeing the chondrules that constitute those rocks. And you can see here that there is a lot of black material. It's the very fine-grained matrix that appears because the thin section is 30 microns thick. And you've got grains which are 1 micron in size. It diffuses the light in every direction, so it appears dark. So you've got a lot of matrix here, whereas you have many more chondrules here, which are all transparent little beads. And if you look at this rock, you've got a lot of black materials. Also, the chondrules are much, much smaller. So that tells you that there was some physical process that was sorting this chondrule and this matrix material inside the protoplanetary disk. And once again, if we manage to elucidate those processes, they're going to tell us what was happening at the time the planets were forming. Before I go any further, just a few words as to what a chondrule is. We've known them for more than 200 years. They were seen the first time a chondrite was put under a petrographic microscope. And at the time, Sorby said, well, they are like droplets of fiery rain. That means droplets of magma, which crystallize in microgravity. But 200 years later, we know a lot more about them, but we still don't know how they formed. So this is the pretty picture of a chondrule. It's a little sphere, a little droplet, and it's even there's some kind of differentiation inside that rock because you've got the transparent olivine crystal at the center. You've got more opaque, more fractured pyroxene crystal at the periphery. So they understood very early on that it was liquids that crystallized in microgravity. And there's this nice little picture that you can see a guy in the space station that's fooling around with this liquid instead of drinking it. This is water. And now he's putting ink inside it to make it a colored bubble. So blue and red is going to turn green. I don't understand the physics of that. So if somebody explains it to me, I'll be happy. But what I find very interesting, you're going to see little droplets. Oh yes, he puts in aspirin that makes bubbles, and you're going to see little droplets being emitted. Do you see that? And it's, we know that chondrules have lost volatiles, and I always thought of it as a very slow evaporation process from the surface of a chondrule. And in fact, now I realize that gas probably comes out as bubble, and we do have microchondrules associated with big chondrules, so I think they must be emitted that way. But clearly, it's telling us something, but it's hard to understand. To show you how little we know about how chondrules were made, that's a diagram that's about 20 years old or something like that at the end of a chondrule conference. And that's a summary made by an astronomer on how the chondrules were formed. And he thinks it's from the heat that has melted the little aggregates of silicate, made them into droplet, is related to the irradiation by the sun. He thinks they're collisions between planets. They think it's big parcels of matter falling on the disk. They think it's lightning in the disk. And and of course, if we did that diagram now, we would have different hypotheses. So I think it means, one, it must have been a rather nasty place to be there at the time. Two, we had a lot of imagination, but we don't understand anything. We don't even know whether the planets were formed already when the chondrules form, and they're the product of collision between planets, or whereas the chondrule formation was the event that initiated the planetary formation. That's how little we know. But of course, we're looking at events that took place 4.5 billion years ago, and that were over-reprinted by many, many events since. So we're still searching. A few more words, and then I'll stop. So you've got a slab here of a meteorite showing you chondrules. And the matrix that's in between, the dark material. And then you've got those little whitish parcels of aggregates. And these are the older objects that we know in the solar system. They're called refractory inclusions. And their age has been measured very precisely. And they are the oldest object we know in the solar system, and they're also made of the least volatile elements. If you took a gas that has the composition of the sun, or the composition of the Orgueil meteorite, and you cooled it down, the first elements that would condense would be titanium, calcium, aluminum, and that's what the refractory inclusions are made of. So we think they are the first condensates made within the solar system, and they are the oldest objects that we can date inside the solar system. So that is the reason we know the age of the solar system and the age of the sun. Corinne told it this morning, said that's the only star of which we actually know the age. We know the age because it's been measured in those little bits of rocks. So that's one thing that is interesting. And then the matrix, I haven't said anything about, except it's grains that are a micron or less in size. In fact, we have a picture here. The scale bar is 200 nanometers. It's very small silicate grains and sulfide grains and metallic grains. And what's interesting in the matrix, it is the site of the volatile elements. I told you earlier that we'd seen different groups of chondrites at different amounts of volatile elements. In fact, those that have the most volatile elements, they are those that have the most matrix. and Orgueil in particular, which is the same composition as the Sun and only very slightly fractionated in terms of volatile elements. We think it's basically made exclusively of matrix. So the matrix contains the volatile elements. It contains organic material, which we're interested in particular in this core because they may be related to the origin of life. And it also contains little grains that were condensed in the vicinity of stars that have disappeared since, like those grains here, which is micron in size. Here you've got a little diamond grain, and here you've got a grain of carbide, a grain of graphite, with the titanium carbide inside its center. And so we think this grain has first the titanium carbide condensed, and then on top of it the graphite condensed. And these grains are inherited from stars that ejected them into the interstellar medium before the Sun and the solar and the protoplanetary disk were formed, so that they are trapped inside meteorites and they reach us whole and we find them. So by studying these grains, and there's very specific isotopic composition, we can relate them to the nucleosynthetic processes that take place in stars and study nucleosynthesis directly. And now this is a whole branch of our discipline, basically people who go and measure isotopes inside those very tiny grains and try to match them to different types of stars and say these grains come from a giant branch, this grain come from a supernova. It's not a separate branch from our discipline, but it's basically people who really work with nuclear physics. Just a few more words. I said earlier on that the surface of the Earth must have been melted over a high depth. So basically all the volatile elements that were at the surface of the Earth must have disappeared. But we have water on top of the Earth. So where does that water come from? There are basically two hypotheses, and we don't really know. What we know is the composition of that water in terms of a D/H ratio. If we compare the composition of the Earth with that of the protosolar nebula, which we see, for example, in Jupiter, it has a lot more deuterium on the Earth. And for a long time, people thought comets, which were very rich in ice, were bringing the water on the surface of the Earth. What we know now is the Earth is the only thing that's really similar to the Earth is the carbonaceous chondrites. And so we can think of two ways, basically. Either carbonaceous chondrites that fell on the surface of the Earth brought water and with them, and of course the oceans, they're very, very thick and it's a lot of water, but compared to the mass of the Earth and to the volume of the Earth, it's very, very tiny. The other option is that the Earth accreted with the water. The rocks that formed the Earth originally, they contain water, and that water's been lost from the first 1,000 kilometers depth, but then it came out again, and clearly we don't know. And last thing is, where do the organic material come from? As you know, there are symmetrical, some of the organic molecule, amino acid and also sugars, they exist in different forms, which we call the enantiomères, which are symmetrical, like the two hands. And I think I'm not going into any detail because this is things that I suppose that you know. But what is important to know is that in life, only 20 amino acids are used in the living organism that we know on Earth. And if they have symmetrical properties, which is not the case of every amino acid, but if they have symmetrical properties, it's only the left enantiomere that is known. But in meteorites, we find many more amino acids. We find 70 instead of just 20 used in life. And some of them, and they are distributed with the left form and the right form almost equally. So what it tells us is that the molecules that generated life, they may have been life as we know it clearly cannot have generated the molecules that are found in meteorites. However, meteorites may have been the source of the life as we know it. We cannot go any further than that from what we know from meteorites. And to conclude, what I want to say is here is a view of the solar system seen. It's a cut slab with the sun at the center, and this is the protoplanetary disk, where you're very hot close to the sun when it just formed, and here you're very far beyond the line where it's not that hot, the ice is evaporated, so you've got ice over there. So this is basically unmodified interplanetary material. So here, probably the whole protoplanetary disk was vaporized, whereas here you've got basically interstellar material that was preserved. And what's interesting is we think that refractory inclusions came from that part. That matrix is basically coming from that part, and chondrules either came from there or they formed later here. What's interesting is inside chondrites you find all these material that are gathered together. And obviously, if we were able to understand the formation of each of these objects, we would be able to reconstruct the whole story of the formation of the solar system. Inside meteorites, we've got basically signature from every single one of these events. You know, when you had external stars that were forming grains, which are still found in meteorites. We've got examples of things that took place when the planets were first condensing, like refractory inclusions, chondrules, and metal grains. They probably date back from the very early epoch of the protoplanetary disk, and then you've got objects that melted later on. So these meteorites, they tell us bits of all this story. It's just difficult to put them together. And that's about it. Corinne told us about all these events this morning. What I really want to stress is with meteorites, it basically, except for the very, very small grains that we find in stars, we're really confined to the 4.6 latest billion years, so the last third of the history of the universe, and a very small area, if I may say. Thank you.